Hello everyone, today I will be explaining / solving chapter 1 of the course division questions for chemistry, which is basically about significant figures and calculations, so it's not super hard, it's easy to grasp. Okay, for significant figures, there are just a couple of rules you need to remember. Zeros to the left, never count. Just remember that, zeros to the left, never count. Zeros to the right, they only count whenever you have a decimal point in the number. So if there's no decimal point in the number, you ignore zeros to the right, okay? So let's start. For part A, there are zeros to the right, which these two here, right? And there is a decimal point in the number, so you count zeros to the right. So in part A, it is 3 significant figures. For part B, you have zeros to the right, but you do not have a decimal point anywhere in the number. So you ignore the zeros to the right, so it's only one significant figure. For part C, there is a 0 to the right and there is a decimal point, so you count the 0 to the right as one of the significant figures. So part C has 2 significant figures. Part D, there's a decimal point, there are 2 zeros to the right, you count them because there is a decimal point. So part D has 5 significant figures, okay? Part E, it says 28 students. Whenever they say like a number of students, number of books, number of tables, it's a discrete number. Means you can't have like 5.5 students, right? It's a set number, like you can only have 1, 2, 3, you can't have half. Whenever it's a discrete number, the number of significant figures is infinite. Just remember that, it's a rule. For part F, okay, there are 2 zeros to the right, but there is no decimal point anywhere in the number. Okay, so part F is 3 significant figures. Now, for number 2, it's just calculations. So, they gave us the mass of the empty flask, mass of flask filled up with water, density of water, volume of the flask. Volume is mass over density. So they want the volume of the flask, which is basically the volume of the water that's in the flask. It's the same thing, right? The volume of the water that's in the flask is equal to the mass of the water that's in the flask over density of water. Mass of the water that's in the flask is equal to the mass of the flask filled up with water minus the mass of the empty flask. So it's 321.01 minus 121.01 over the density, which is 1. And you end up with 200. And to check how many significant figures you reported to, you look at the values you used. For this one, 5 significant figures, 5 significant figures, 3 significant figures. So your answer should be reported to the least number of significant figures, which is 3, which is why we leave it at 200 centimeter cubed, okay? For the next part, we have the mass of the flask filled up with CO2, and they want mass of CO2 in the flask. So the way to do it is you do mass of the flask filled up with CO2, 123.2, right? Minus the mass of the flask, itself, which is 121.01. Alright? And the answer you get is 2.2 grams. Okay? For the next part, they want us to find the number of moles in CO2. Formula for number of moles is equal to mass over molar mass. Mass is 2.2. Molar mass of CO2 is 44. So number of moles is 0.050. This is 2 significant figures because you use 2.2, which is 2 significant figures, right? Number of moles, so 0.050 moles. Okay, next, they give you the temperature and they want you to find the pressure. So how do you find pressure when you have number of moles, temperature, volume? You use the formula PV equals nRT. Okay, so PV equals nRT, right? They want you to find pressure, so you move volume to that side, so P equals nRT T over V. So you solve it and you end up with 6.2 atmosphere. Alright? Now next question. Okay. Let me just clear this. Okay. In a laboratory session, okay, we don't need to read that part. Okay. So there's a flask with a volume of 1000 milliliters, so 4 significant figures. They filled the flask with dry air and measured its mass here. They filled the flask with unknown gas and measured its mass here. Measured the temperature, measured the pressure of both gases, found the density, which is of dry air, which is 1.19. Okay, first thing they need us to find is the mass of dry air. How to find the mass of dry air? Here, I'm over here. Okay, mass of dry air is equal to density of dry air times the volume, right? Density of dry air was given to us right here, 1.19, right? It's 1.19 times the volume, which is 1000 milliliters, which you change to 1 liter. Okay? So you end up with 1.19 grams. That is the mass of dry air. To find the mass of the closed flask, they gave you the mass of the flask with dry air, which was 157.7, right? And you have the mass of dry air. So all you do is 157.70 minus 1.19, right? And you end up with 156.51. That is the mass of the flask. Okay, part C, find the mass of the unknown gas in the closed flask. Where is it? Here. Okay, they gave you the flask with the unknown gas, and you have the flask, the mass of the flask. So to find the mass of the unknown gas, you just do the mass of the flask with the unknown gas, and you subtract it with the mass of the flask itself, right? And you get 1.57 grams. Okay? Now, to find the molar mass of the unknown gas, you have the pressure, you have the volume, you have the mass. We can get the molar mass, and the formula that we can use for this is PV equals nRT. Okay, so you do PV equals nRT, but we don't have n, so we substitute it with, mass over molar mass, right? Over RT. What are we trying to? We're trying to find the molar mass of the unknown gas. So we cross multiply mass to the other side, molar mass to the other side. You end up with mass times R times T over PV. Mass, you have it, we got it from here, 1.57. R is 0.082. Temperature, they gave it to you 25 degrees Celsius, you change it to Kelvin. Actually, I'll just write this down for you guys. It's 1.57 times 0.082 times temperature, which is 25 plus 273, which is 298, over pressure, which is 850 millimeter mercury, so you change it to atmosphere. It's 850 divided by 760 times the volume, which is 1, and you end up with 34.3 grams per mole. Okay, now for the next part, they want us, when all the students finished their calculations, the teacher announced that the unknown gas is HCl, molar mass 36.5. Find the percent error. Okay, the molar mass that we got was 34.3. to calculate the percent error, we do the actual value minus the value that we got over the actual value times 100. That is how you find the percent error, and you end up with 6.0%. Okay, that is the percent error. Now, new page. Okay. Two possible scenarios were suggested by the teacher to explain the variation between experimentally determined and actual molar mass. Okay, so they gave two scenarios, and we need to see if it's true or false that these scenarios are possible, given that the molar mass that we got was less than the actual molar mass. So it's saying here, the HCl did not replace all the dry air, and therefore some of the dry air was still in the flask. Okay, mass of dry air is 29 grams. Okay, mass of the dry air. Mass of the HCl is 36.5. Right? If some of the air was left off in the flask, then that means it would bring the molar mass down, right? So, and the molar mass that we got was less than the actual molar mass of HCl. So it did bring it down, so that's correct. That is a possible scenario. Second scenario, the temperature of dry air was 25, but the temperature of HCl was less than 25. Okay, for the second scenario, they're saying the temperature of the dry air was 25 degrees Celsius, but temperature of HCl was actually less than 25. Density, it increases with decreasing temperature. So if the temperature is lower, then density would be higher. Okay, so they're saying the temperature was actually lower, so when you do mass equals density times volume, and the temperature is lower, density is up, which means the mass would also increase, so it would be greater than 36.5, right? It would be greater than it. The mass that we got was 34.3, which is less than 36.5, so that's not valid. If the temperature was less, density is higher, and the mass should be higher, but we got the mass to be lower, so the second scenario is not valid. Okay? Now, for part G, how can the students experimentally prove that the volume of the used flask is indeed 1000 milliliters at 25 degrees Celsius? Okay, there are two methods. I'll just say the easier method. You can use a 1000 milliliter graduated cylinder to measure 1000 milliliters of a liquid, transfer that liquid into the flask, and then check if the volume of the liquid that you added is equal to the volume of the flask itself. If it measures exactly, that means that is the volume of the flask. Okay? Now, number 2. Students were given a hydrate of copper 2 sulfate, CuSO4.NH2O. That's what hydrated means when it's .H2O. And were given the task to find N, the water of hydration. To do so, the students follow the following steps. They gave you the mass of the crucible. They gave you the mass of the sample and crucible together. They heated the crucible for 5 minutes once, they heated it again for 5 minutes, and they heated it a third time for 5 minutes, and then they found the mass at each time. Okay? For part A, they're asking, why did the students heat the crucible only 3 times? It's because the mass after the second heating was this, and the mass after the third heating was this. The difference is very minimal, so they didn't have to heat again because they would get the same answer. Okay? For part B, deduce the formula of the hydrated copper sulfate. Okay. First step is you find the mass of the water evaporated. So the mass of water evaporated would be the mass of the sample after the heating minus the mass of the sample before the heating, right? Because after heating, water evaporates. So before the heating, the water is present, so that's how you find the mass of the water that evaporated. So you do 48.281 minus, what is the mass of it is 48.659. Okay, this is the mass of, oh wait, did I use the wrong value? Oh, sorry, it's supposed to be the other way around. 48.659 minus 48.281, sorry. You get 0.378. That is the mass of water evaporated. Okay, next step, you find the number of moles of the water. So number of moles is equal to mass over molar mass. So you do 0.378 over molar mass, which is 18, and you end up with 0.0210 moles. That is the number of moles of water. Now you need to find the number of moles of CuSO4, which is copper sulfate, so you can get the mole fraction. I'll show you. Okay, so to find the number of moles, first you need to find the mass of CuSO4. Okay, the mass of CuSO4, the way to get it is, after heating the sample plus crucible, all that's left is CuSO4, because, is it CuSO4, sorry? Yeah. All that's left is CuSO4 because the water was evaporated. So this is the mass of CuSO4 plus the crucible. So you subtract it from the mass of the crucible. So you do 48.281 minus 47.599. The mass you get is 0.682. Then to find number of moles, you do 0.682 over its molar mass, which is 159.61. You get it from the periodic table, and you end up with 4.27 times 10 to the minus 3. Okay? Here. So this is the mole of this number of moles of CuSO4. This is the number of moles of H2O. So then you do the mole fraction. So number of moles of H2O over number of moles of CuSO4. Okay, so you do 0.021 over 4.27 times 10 to the minus 3. The answer you get is 4.91, which is approximately 5, right? So the mole fraction, so basically the ratio of H2O to CuSO4 is 5. So the formula here would end up being CuSO4 times 5H2O, because that's the ratio, right? So N would be 5, okay? In some groups, heating the solid led to some of the solid splattering out. How will this affect the calculated mass of evaporated water? Okay, basically, you wouldn't know that the solid splattered out, so you would count the loss in mass as water evaporated. Thank you for watching, and I hope you understood everything. If you didn't, just feel free to ask me, okay? Thank you, bye.